example 2. Okay. Example 2. Let's check to see if the critical values of example 1 are local extrema, or local maxes or mins. So again, just because they're critical values, that's not a guarantee. We have to check to see if they're local maxes or mins. Okay, so we had, excuse me, we had the fact that f of xy is equal to x plus y times the sine of x. Okay, and we had critical values. I don't know what it is with my h's here. We had critical values 2n pi negative 1 and 2n plus 1 pi 1, and defined for all n in z integers. So we have a bunch of critical values. We have 0, negative 1, we have 1, you have 2 pi negative 1, 4 pi negative 1, and then we have pi 1, 3 pi 1. So we have an infinite number of critical values. We need to see if any of those are local maxes or mins. Well, pick a value. Just sort of pick one at random and work with that, subject that one to analysis. So that's what we're going to do. So just pick a critical point. And check the value of the function. That's what you're doing. That's how you check maxes and mins. And to check the value of the function in a small region, in a small ball, in a small region, ball or disk, around that point. Around that point. And that's how we're going to check, right? I mean, the definition of a local max is if I have a point P and if there's a certain value for the function f of P there, if I sort of move to the left or right, this way or that way, then the values that I get should be either all less than f of P or all greater than f of P, and that'll tell me if it's a local max or min. And that's exactly what I'm going to do. So now, in subsequent lessons, in the next couple of lessons, we're actually going to devise ways of handling this local max-min business more systematically. But oftentimes, in this case, we just want to get used to analyzing the function, just sort of taking a look at it, get familiar with it before we develop the systematic tools for deciding whether something is a local max or a local min. You remember from single variable calculus, we took the second derivative to find out if it's concave down or concave up. There are analogous things like that, and we'll develop them. But right now, we just want to do it by observation. Which is really, really important to be able to do. When everything is said and done, it's about how familiar you are with the function and being able to analyze it using other tools at your disposal, all the things that you know. So, okay. So now let's just choose 2n pi 1 with n equals 0. So I'm just going to pick the easiest point. So 0, negative 1. So that's going to be our critical point P. Well, let's go ahead and find what the value of the function is at 0, negative 1. So the function is x plus y sine x, so it's 0 plus negative 1 times the sine of 0, which is 0. So the value of the function there is 0. Okay, so the first thing I'm going to do, well, since we're dealing with a two-dimensional domain, okay, we're dealing with R2. So I'm over here. So what I'm going to do is I'm actually going to, so we have x and y. Well, I need to check both. So what I'm going to do is I'm going to actually hold one of the variables fixed, and then I'm going to just move the other one. In other words, I'm going to move a little bit in this direction, and I'm going to move a little bit in that direction to see what the function does. If I get my answer, great, I can stop there. If not, I'm going to hold the other variable. I'm going to hold x fixed, and I'm going to move a little bit in the y direction that way, and I'm going to move a little bit in the y direction that way to check to see what happens to the function. And hopefully those movements will tell me what's going on. So that's what I'm going to do. So I'm going to decide to hold, so let's hold y fixed first. And we'll vary x. So what I'm going to do is I'm going to hold y fixed, and then I'm just going to move a little bit this way and a little bit that way around x. Let's vary x about 0, because 0 was the point where we are. So I'm going to move a little bit to the right of 0, a little bit to the left of 0, and see how the function behaves. Okay, well, let's take x equals 0.1. So let me move 0.1 in that direction. Then f of 0.1 minus 1, because we're holding y fixed, it's going to end up giving me some number which is positive 1.7 times 10 to the negative 4. Okay, so it's a positive number. Well, now I'm going to move in the negative direction. Let's take x equal negative 0.1. Then f of negative 0.1 negative 1, that when I do that one, evaluate that, I'm going to get minus 1.7 times 10 to the negative 4. So basically what's happened is this. This is the value of my function at 0, negative 1, okay? Looking at it from just 1. So I'm holding y fixed. So now what I'm looking at is just the x-axis this way. If I moved in the positive direction from 0, my function actually went up. So the value of my function is 0 at 0, negative 1. So the value of my function actually became positive. When I moved to the left, the value of my function became negative. So in this particular case, this tells me everything that I need to know. I don't actually need to do the next check. I don't need to hold x fixed and work on y. This right here tells me what I have is some kind of a point of inflection, okay? In order for it to be a local max or min, it would need to be like this for a local min, or like that for a local max, but that's not what's happening. So as I move around the point 0, negative 1, in the x direction holding negative 1 fixed, I end up with a point of inflection. So essentially, I've turned it into a single variable problem. Because that's the case, it's neither max nor min, and that's what this tells me. So this is neither max, I should not say neither max nor min. There is no local max or min. So in this particular case, there is no local max or min at these critical values. So the derivative might equal 0 there, but it doesn't actually achieve a maximum or a minimum there, because with this simple analysis, we've discovered a point of inflection, some sort of a point of inflection. So that's all that's happening here.